А где эта ссылка должна находиться?
Там вот
Аня, добрый
дополнительно...
день.
Да, здравствуйте. Дополнительно 3 точечки, и вот по ней
У меня
запустить. Да, они просто теперь у вас уже пропали.
Аня, добрый день. Так, нас слышно?
Да, вас
Слышно.
Отлично. Отлично.
Да,
Все,
всё,
Александр.
Слышно.
Трансляцию я запустила.
На трека.
Ну, хорошо.
Аня, добрый день.
Да, здравствуйте. Дополнительно 3 точечки, и вот по ней запустить. Да, они просто...
Это-то я
Так,
помню.
Аня, нужно перейти куда-то.
Куда?
Или здесь оставаться.
Для чего? У вас доклад в этой сессии?
Не, сейчас вот Александр Сергеевич будет ведущим. Значит, все, мы пришли правильно, да?
Все, да, значит, вот председатель на месте.
Председатель.
Да.
Да.
Олечка, пошли.
Анна, видимо, меня нужно сделать хотя бы с организатором.
Я вас обратно сделаю организатором, и я тогда отключусь.
Хорошо.
Я надеюсь, что...
А Дмитрий Викторович,
Теперь у вас
а кто будет?
на месте.
Председатель.
Да.
Так, YouTube идет. 2 минуты до начала работы секции, да? Татьяна Владиславовна, вы, наверное, можете видео пока включить.
Обязательно видео?
Ну, это приветствуется. Это не обязательно, но...
Ну, во время доклада-то, наверное, не обязательно.
Это у нас
Удобнее всего. Но это ваше дело. Главное, чтобы доклад было видно.
Хорошо. Вася, ты не уходи, Вася. Да. Я готов.
Александр Сергеевич, начинаем?
Ну что, начинаем уже, да, можно?
Да.
А я вот не вижу
Я
доклад.
начну и представлю вас как организатора.
Пожалуйста.
Dear colleagues, dear participants of the conference, my name is Alexey Yeremin, and I'm a moderator of this session. In this session, 4 talks will be given, and there are some basic rules. All presentation will be given in English. There are 12 minutes or less to make every presentation, and 3 minutes we have for questions. 2 minutes before 12 minutes are finished, I will inform the speaker about this. During the presentation, all the audience will be muted, but after the presentation, you can unmute your mics and pose a question. There are also questions possible to be given through chat and through the YouTube translation. So there is, every one of you can find out the link to the YouTube translation broadcast, and you can share them with your colleagues who are not allowed to be in the Zoom room. I will repeat the same in Russian. Дорогие коллеги, участники конференции, меня зовут Алексей Еремин, я модератор этой секции. На секции будет дано 4 доклада, все доклады делаются на английском языке. Время на доклад не больше 12 минут, 3 минуты будет дано у нас на вопросы. Вопросы можно будет задать после, если вы хотите это сделать сделать голосом, также можно задать вопросы через чат или через чат трансляции в YouTube. Ссылку на YouTube вы видите сверху и можете поделиться ею со своими коллегами, которые не получали ссылки для очного участия в конференции. The session is chaired by Professor Alexander Shmirov. Alexander, please.
Сергеевич, Так, hello, dear colleagues. I'm glad to welcome all the participants of our section. Our section is called Mechanical Systems Control. I hope that all speakers are present. The first report is called Representation Form of the angular velocity vector for an orthonormal basis of a moving frame. The report will be made by Vlasova Tatiana Vladislavna. Please start.
Thank you. Hello, dear colleagues. One minute. I will talk about representation forms of the angular velocity vector for an orthonormal basis of a moving frame. There exist different ways for introducing the concept of the angular velocity vector of a moving space. For example, you can find an explanation of the angular velocity in terms of the Euler angles or other angles, of rotation matrices, and others. My co-author and I propose the approach based on the construction of a general solution of kinematic equations for a moving basis in the vector form. Ideas for this approach are outlined in the following publications. In presented study, we have obtained 5 different forms of the angular velocity vector for an orthonormal basis of a moving space. You can see them on the slide. Problem statement. In the absolute space, another space with its own reference frame moves. We will call it a moving space. Let EI be the basis of this frame. This basis is called the moving basis. The orientation and the motion of this basis in the absolute space is given by the following equations. Here, EI are vector functions twice continuously differentiable for all t in G. For each t, the moving basis forms the right orthonormal triple of vectors connected by relations from number 1 to number 5. Our aim is to demonstrate the existence of 5 possible representation forms for the angular velocity vector of a moving space and to construct them explicitly. To do this, we construct kinematic equations of the motion for each of the basis vectors, a system of kinematic equations of the moving basis, a solution to this system. At the end, we get different representation forms for the angular velocity vector. The kinematic equation of the basis vector is the equation connecting the motion and the velocity of this vector. From equality form, it follows that vectors of the motion and of the velocity for the basis vector are orthogonal to each other for any t. Then for every t, there exist vectors omega I, connecting them by equality 6. The vector function omega I, we call the solution to the ith equation 6. The equation itself, we call the kinematic equation of the ith basis vector. The set of solutions of the ith equation 6 we denote by capital omega I. Let us combine equation 6 into system 7. Here, the vector omega is the same to each of equation 6. This vector we call the solution of system 7. In system 7, either a non-unique solution may exist or it may not exist at all because system 7 is redundant. System 7 connects 3 vector equations under constraints from number 1 to number 5. The set of solutions to system 7 we denote by capital omega. Any solution of system 7 is a solution to each of 3 equations in system 7. Every element of the set capital omega we call the angular velocity vector of the moving basis. A necessary and sufficient condition for the existence of a solution to system 7 is the fulfillment of relations 4 and 5 on velocities of the basis vectors. This solution is unique and has the form 8. In this study, we have obtained form 8 in a slightly different way than in our previously published papers. The vector omega 1, defined by 8, is the first representation form of the angular velocity vector. Now we transform equality 8 and construct 4 more forms for the angular velocity vector. To do this, we introduce vectors number 9 and number 10. In this notation, equality 8 takes form 11, and using vectors 10, it can be represented in 3 ways 12. Vectors gamma I can be obtained explicitly. Let us show this. It is easy to see that every vector gamma I is collinear to the corresponding basis vector. Then we can write equalities 13. From 13, it follows that equalities 14 hold. Using notation 9 and 10 and equalities 1 and 5, we obtain 15. Substituting 15 in 13, we get explicit expressions for gamma I. You can see equalities 16. Now we substitute 16 and 9 in the right-hand sides of expressions 12 for the vector omega 1 and denote them respectively omega 2, omega 3, and omega 4, equalities 17, 18, and 19. Given this notation, we get 3 more variants of the representation form for the vector omega 1. So we can write equalities 20. Now we construct the 5th form for the vector omega 1. Let us recall form 8. Using notation 9 and equalities 11, 1, and 5, we get the following 3 equalities, 21, 24, and 23. Therefore, we obtain equality 24. Comparing its left side with 11, we get equality 25, where omega 5 has form 26. It is easy to show that equality 25 for omega 1 can be constructed via any of 3 equalities 20. So we have equalities 27. These results can be summarized as follows. All vectors omega 1, omega 2, omega 3, omega 4, and omega 5 define the same angular velocity vector of the moving frame in the absolute space. Thus, we can write equalities 28. The following 2 slides contain figures of the vector omega constructed using forms 17, 18, 19, and 26. In all the figures, we introduce notation 29. On this slide, you can see the angular velocity vector constructed in forms 2 and 3. On the figure 1, the vector omega is constructed as the sum of the vectors omega 0, 1 and OA1. On the figure 2, the vector omega is constructed as a sum of vectors of omega 0, 2 and the vector OA2. These vectors are already in other planes. The vector omega is the same vector on the both figures. It is the diagonal of a parallelepiped with sides OA1, OA2, and OA3. This slide illustrates the angular velocity vector constructed in forms 4 and 5. We can conclude our presentation by the following. Each of the constructed vectors, omega 1, omega 2, omega 3, omega 4, and omega 5, is a solution to each equation of system 7 separately. The moving space has a unique angular velocity vector. Thus, the vector omega 1 is the angular velocity vector of the whole moving space, despite the choice of the moving frame. All the obtained results can be easily transferred to a solid body. For this, a moving space is conditionally considered as an absolutely solid body, and the reference frame is considered as a Cartesian coordinate system that is rigidly attached to the solid body. We believe that the form omega 1 is the most convenient for using in the theoretical research. The other forms may be useful when considering practical problems. References, well, that's all. Thank you for your time.
Yeah, dear colleagues, you now can unmute your mics and ask the questions.
Any questions?
Yeah, it's time for questions.
No more questions. Okay. Thank you. The next report is called Space Robot Control System for Long Distances. The report will be made by Yefimova Polina. Please start.
Good day. I want to present to your attention a report on the topic Space Robot Control System for Long Distances. As a way to remote control a robot, the bilateral system is most often considered. The bilateral control system is a force feedback remote control system. In the classical case, it is represented as a master-slave system. The system is subdivided into two sides, the operator side and the remote side. On the operator side, there is the human operator and the master robot. On the remote side, there is a slave robot and a working environment. A human observing the objects of the working environment through the displays interacts in the required way with the master robot, moving its working tool in space and transferring the necessary forces of interaction with the objects. The slave robot repeats these motions and transfers the reaction force of the objects to the operator side. Data transfer between system objects is shown in figure. The time delay in the transmission of the control signal has a significant impact on the quality operation of a bilateral system. There are three main approaches to building a delay-tolerant bilateral system: passive system approach, predictive display method, and use of sliding control mode. However, these methods are efficient with delays of no more than 4 seconds, which complicates their application for space missions. In this regard, the urgent problem arises of constructing such a bilateral control scheme that would be efficient at long distances. As an approach to solving this issue, a method of remote control of a robot by teaching future actions is proposed. The process of controlling a space robot using leaf method can be divided into 4 stages. At the third stage, the space robot using sensors collect the necessary information about the working environment and transmits it to the control center. At the next stage, based on the data obtained, a full-scale model of the remote environment is formed. At the third stage, operations are worked out. The control takes place as in the traditional method of bilateral control without delays, where an industrial manipulator with 6 degrees of mobility acts as a slave robot. The motions of the instrument are memorized and transmitted to the space robot. If necessary, the space robot can be displayed for a human operator wearing augmented reality glasses. At the last stage, the space robot works out the obtained algorithm of actions while adapting to possible changes in their working environment and transmitting a report on the work done to the control center. If the control center has confirmed the success and completeness of a mission, the stages are terminated. Or otherwise, the cycle is repeated until the required operation is completed. The main objective of this work is the construction of mathematical models of space and auxiliary ground robots, as well as the development of a method for adapting to changes in the working environment. To accomplish this task, it is necessary to solve the following subtasks: forward kinematics problem, inverse kinematics problem, forward instantaneous kinematics problem, inverse dynamics problem, the task of adapting a robot to environmental changes, and software implementation. As object to research, we will consider a free-flying space robot, which is a body freely movable in space with a free link manipulator installed on it, as well as an auxiliary ground manipulator, for which we take the kinematic scheme of the Fanuc M20IA manipulator. This slide shows a kinematic scheme of a space robot. The mechanical system consists of 4 bodies, a base, and 3 links. The motion takes place in an absolute coordinate system, analogous to the absolute system of a ground robot. In our case, the characteristic point are the center of mass of the base, the attachment point of the links, and the characteristic point of the manipulator tool. The kinematic scheme of the Fanuc ground manipulator is built in a similar way. It consists of 6 links and its base is motionless. We represented the solution of the forward kinematics problem in terms of homogeneous transformation matrices. T is a homogeneous transformation matrix between 2 neighboring coordinate systems. It includes a rotation matrix and vector of displacement of one coordinate system relative to the other. In this case, the position of the characteristic point of the space robot instrument in the absolute coordinate system will be determined by Formula 1. This slide shows the solution of the forward kinematic problem for a space robot for given initial and final values of generalized coordinates. The solution of a forward kinematics problem for a ground robot is carried out in a similar way according to Formula 2. This slide shows the solution of the forward problem for a ground robot for given initial and final values of generalized coordinates. Where inverse kinematics problem is to determine the generalized coordinates of a robot by the given Cartesian coordinates of the characteristic point of the tool and its given orientation in absolute space. Let us present the solution of an inverse kinematics problem for a space robot. Let us consider separately the problem of bringing the tool coordinate system to a given orientation without considering the equation of the final position of its characteristic point. The specified orientation of the tool can be provided with 3 angles of rotation of a link. Their values given through the null components of the matrix of the desired orientation are found by the method of inverse transformations. The task of bringing the characteristic point of the tool to a given position can be solved by knowing the coordinates of the tool point after turning it into the required orientation. In this case, the linear generalized coordinates of a robot body should shift its center of mass by the vector of the difference between the desired position and current. In this case, the generalized coordinates Q4, Q5, and Q6 will be found by following formulas. The solution of inverse kinematics problem for a ground robot was carried out by the geometric method, where values for the first 3 angulars are presented on this slide. Here is the solution to the inverse kinematics problem for coordinates Q4, Q5, and Q6 of the ground robot. This slide shows the solution to the inverse problem for space and ground robots. The forward instantaneous kinematics problem establishes a connection between the linear and angular velocities of the links with a vector of generalized velocities. The relationship between them can be expressed through the omega large and V large matrices. They are calculated using the recurrent formulas 3 and 4. Let us introduce the concept of Plücker coordinates of a velocity into consideration. The Plücker coordinates of a velocity of the ith body is a 6x1 vector, the first 3 component of which are the projection of the angular velocity of ith body on the axis of the associated coordinate system. The next 3 components determine the projection of a linear velocity of the pole of the ith body on the axis of the same coordinate system. When the equation for the relationship of angular and linear velocities with the vector of generalized velocities can be written by Formula 5. There, the matrix C will contain all the coupling matrices. The derivation of the equations of motion for the robot was based on the Lagrange equation of a second kind. The kinetic energy of a system is determined by Formula 6. Matrix B here describes the mass inertial characteristic of the system. Substituting equation 6 into the expression for the kinetic energy, we obtain formula 7, which describes the kinetic energy of a system in terms of generalized coordinates and generalized velocities. Further substituting the value of kinetic energy of a system into the Lagrange equation of a second kind, we obtain the robot motion equation according to formula 8. Let us present the values of the generalized forces of space and ground robots that provide the following law of change in generalized coordinates. On the right are the initial and final vectors of the generalized coordinates of the space robot and the law of motion. On the left are similar data for the ground robot. Here are the graphs of a change in the generalized forces for a space robot. This slide shows graphs of changes in the generalized forces for a ground robot. As a method of adaptation to environmental changes, a method is proposed in which characteristic points of a working surface are formed using laser rangefinders. Here they assume that the change in the environment consists only in its displacement and rotation relative to its initial position. For the practical implementation of the effect of combining characteristic points corresponding to each other in the control process, it is advisable to use in the law a term that is a function of a mismatch between the desired and current vector of the position of the characteristic points of the external environment and normalize it by the number of points. And to maintain the vector of force of interaction of the working tool with objects of the external environment, Q, close to the desired QD obtained during training, it is necessary to use in the control law. In addition to the above, a term that is a function of a magnitude of the mismatch between the vectors Q and QD. The resulting control law is described by formula 9. The result of the study is the construction of a kinematic and dynamic model of space and ground robots, which are the foundation for future research of a bilateral control system by showing future actions. List of used literature. Thank you for your attention.
Okay.
Colleagues, I think that Noboru Sakamoto has a question. Noboru, please turn your mic on.
No questions. A question. Okay. The next report is called Attitude Controlled Motion in neighborhood of the collinear elevation point L1. The report will be made by Shimanchuk Dmitry Viktorovich.
Colleague,
Please start.
I think that you hear me. Is it true? Dear colleagues, my name is Dmitry Shimanchuk. The topic of my presentation is attitude controlled motion in. Oh, sorry.
We don't see your presentation.
Sorry. Okay. Dear colleagues, my name is Dmitry Shimanchuk. The topic of my presentation is attitude controlled motion in a neighborhood of the collinear elevation point L1. There are two general parts to consider: the equation of attitude-controlled motion and numerical modeling and result. An attitude motion relative to the center of mass depends essentially on the position of the celestial body's center of mass in outer space. However, on the other hand, an orientation of a celestial body can affect to orbital motion. For example, the orientation of a solar sail can change the resulting light pressure vector and thus directly affect on the solar sail orbital motion. The work deals with the attitude motion of a celestial body of mass m, lowercase, in the gravitational fields of two attractive center, the Earth of mass m1 and the Sun of mass m2. Inequality is satisfied. Such a motion of the celestial body can be described by the mathematical model of the circular refractive three-body problem. It is known that the equations of the refractive three-body problem have 5 scenario solutions, which in celestial mechanics are called libration point or Lagrange point. Collinear libration point L1, L2, L3 unstable equilibrium position. Triangle libration point L4, L5 are stable equilibrium position over a certain mass ratio of attraction center. This stability condition in the linear approximation can be represented in form. You can see this in slide. To study the motion of the celestial body, we introduce the following system of coordinates. O, X, Y, Z overlined uppercase is a stellar system, stellar frame with origin fixing at the center of mass of the S and the Sun. O, X, Y uppercase with overline is the plane in which the orbit of the Earth and the Sun lie. M1 X Y Z uppercase is a rotation frame. C X Y Z uppercase is the orbital system of coordinate with the origin at the center of mass of the body, and the axis parallel to the axis of the rotation coordinate system. I sub I from 1 to 3 are its basis vector. C X Y Z lowercase is a frame rigidly connected with the body and the origin at the center of mass of the body. E sub I from 1 to 3 I its basis. And the axes are directed along the main central axis of inertia of the body. The orientation of the celestial body with respect to the X, Y, Z will be determined using the Rodriguez-Hamilton parameters lambda sub I from 1 to 4 by the relation 1. through the Rodriguez-Hamilton parameters, one can uniquely determine the metric of the direct cosinus of the basis vector. E sub I and I sub I. You can see it is 2. If the center of mass of the celestial body has fuzzy coordinates of the libration point L1, then the dynamic equation of the colibration of the controlled rotational motion of the celestial body relative to the center of mass are 3. For the projections of the rotation of a rigid body around the C, X, Y, Z on the axis of the frame C, X, Y, Z lowercase, we consider the quaternionic kinematic equation of rotational motion in the metric form 4. The system of the equation 3 and 4 is the closest system of differential equation which describes the celestial body attitude control motion at the libration point L1 in near S space. We assume that the center of mass of the celestial body is at the libration point L1. Then there can be a motion in which the coordinate system C, X, Y, Z lowercase and C, X, Y, Z uppercase are coincide. It is mathematically represented as 5. It can be shown that in the framework of the problem of studying the dynamic of the celestial body in the gravitational field of the true attractive center when Ix and Ix equal Iy, Iy. There is an unlimited set of the relative equilibrium position of a celestial body in the orbital frame. 6. It follows from 6 that for the celestial body whose center of mass has the coordinate of the calibration point, there can be a stationary rotation, so-called Euler case. To estimate the stability of the relative equilibrium position 5 and 6 in the neighborhood of the libration point L1, we linearize the uncontrolled system of antitune motion 3 and 4. Hence, the system of linearizing equation can be represented as follows. To the equilibrium position 5, the matrix R of the analysis system has eigenvalues. You can see in slide. To the equilibrium position, note that for an inert ellipsoid, it is necessary to satisfy the triangle inequalities for its principal central axis of inertia. Its equalities you can see in slide. From that, we can second equalities, which is in equation of motion. an X, an Y, and Z. Thus, for the possible existence of small oscillation with respect to the equilibrium position from the form of the eigenvalues and figure 3, it is necessary that an equality satisfy. We have two cases. For the case of the equilibrium position 6, the matrix of the linearized system has eigenvalues lambda 1 and from lambda 1 to lambda 7. You can see it in slide. From the form of the eigenvalues and figure 6, it follows that small oscillations are possible outside the interval -1, 0 for angular rate R in the regions 1 and 2. The content of the next 4 slides includes formulation of Lyapunov stability theorems. It is related with Lyapunov stability of the stationary equilibrium position, Lyapunov stability of the stationary rotation, Lyapunov stability of the programmed position, and Lyapunov stability of a programmed motion. Let's move on the next part, which is numerical modeling and result. The content of the next 13 slides includes the result of numerical experiment, where you can see time history of the angular rate, parameter Rodrigo-Milton, and more else.
Time to finish.
Okay. I think that enough. Please, your questions, reference, and thank you for your attention.
Okay. Any questions? No questions. Okay. The next report is called. The next report is called an embedded explicit method for patient systems of ordinary differential equation. The report will be made by Alexey Yeremin. Please start.
Okay, dear colleagues, glad to greet you here. Actually, my talk is not about control, but it's always very hard to find out the session for the pure numerical methods. So we have chosen mechanical systems because our method can be used for mechanical systems, and we give one of the examples. And it also can be used for control systems as well. So this is joint work with the Professor Igor Olemskoy, and let me start. So I will remind very briefly about what are Runge-Kutta methods and what are embedded methods and partitioned methods. And we construct a special partitioned method with an embedded error estimator. So when we consider a system of ordinary differential equations, here y and f might be vectors of some length. We usually formulate Runge-Kutta methods as methods formally extended to the system, just replacing the scalar values which are used in its formulation by vectors. Runge-Kutta methods is based on estimating the vector field and combining it with some coefficients to get the addition to the initial value when we move from point x0 to point x0 plus h, where h is called a step size. So there are some extensions of Runge-Kutta methods. One of them is using an embedded pair of methods. They're called embedded methods because they are two different methods, but the vector field is estimated in the same point. So since the most difficult part, the most time-consuming part is finding out the values of the vector field, just getting another linear combination is very cheap, and we have two values, z and z bar, which give us the estimation of the error, or any, if it's not the error of the solution itself, it's anyway some value that give us the basis to change the step size. So partitioned methods is another extension of Runge-Kutta methods to systems. Here, we don't just consider any equation in the system the same, but we divide it into two or more, sometimes components, when we apply different schemes, different methods to each component. They are interconnected, but generally they might be even with different number of stages. It is used when we have, say, stiff and non-stiff parts, and we would like to use explicit methods for non-stiff parts while using the implicit methods for stiff parts, or we may have different values of different physical nature and applying, say, methods with smaller step even for one part and larger step for another part. In our studies, we consider the structure of right-hand side dependencies on the unknown functions. So here we don't consider them to be of different nature or stiff or non-stiff. We just consider, we study how does the right-hand side depend on the unknown functions. In the group 0, which might be vector, every right-hand side depends on every unknown. But in two other groups, which we call structural groups, every right-hand side depends only on the previous functions of this group or on the other groups. So here, zeros mean that the corresponding function does not depend on the unknown. So f1 will not be dependent on y1, y2, and y3. f2 depends only on y1 or other groups. This gives us a possibility to construct explicit methods with fewer stages, with fewer right-hand side estimations than the classical methods that are suitable for the general equations. So the method, as an example, this is a system of Euler equation of rotation of a rigid body. Here we have 3 coordinates, and here y1 and y2 are the values that depend on y1, y2, w1, w2, and w3. And here we have the system which has general equation and 2 equations in the structural groups. So the method that we construct is an embedded pair of methods that have its own scheme, its own coefficients for every equation, for every group at least, and the stage slopes or the vector field is estimated for every equation one by one in a strict direction, strict order. So when we find k11, we already use the value of k01, and when we find any of them, we already use everything we have computed by now. This is similar to the Seidel idea to improve the method of simple iteration. So those are formulas to find out the stage approximations that are used here as an arguments of slopes. And here we have explicit methods, though we have here summation up to the w, not only up to w minus 1, which will be an explicit method formally extended to any system of ODEs. So the order conditions that connect between themselves the coefficients of the method, they are based on that the Taylor expansion of the numerical and the exact solution are equal up to the desired order. So for a classic Runge-Kutta method, for a scalar equation or for a formal extension to the system, the Taylor expansion starts like this, and as you see, for every order of h, we have more and more terms that should be, all of them should be satisfied to have the same coefficients to provide the desired order. And the number of order conditions is rather small. It's 37 equations for a 6th order method that we are desired to construct, and the minimal number of stages to solve them is 7. However, if we want to construct the 6th order method with an error estimation, the embedded pair takes 8 stages. So for a partitioned method, every part here will have different f's, and they can be differentiated in respect of different y's, and it gives us much more order conditions. We have 3 groups and additional equations for embedded method, and the system of order conditions consists of 1,290 equations. And when we use 8 stages for the general group and 7 stages for all other equations, which is the desired advantage we try to construct, it gives us only 320 coefficients to solve the nonlinear equations of 1,290. So the most difficult part of this research was to construct this method, but it will be very useful to show those equations and to tell about how did we solve them. So I will proceed to the method itself. Well, actually, the method itself consists of a big number of coefficients, and I think they don't even can be shown in one slide. So nothing more than other numbers here. So we have constructed one of those methods where generally we have a family of several parameter system, but we have chosen one that will provide us mostly with positive values here. And let me show the numerical comparison of this new scheme to the known schemes. So we have chosen a test problem that have 5 equations, one for each group. I mean, the one for the general group that doesn't have a special structure, and 2 equations for groups I and group J, so that all 9 groups of coefficients will be used here, and we will check that the methods we can have constructed are right. So here we know the exact solution, and we solve the equation with this method, with its formal extension to the system without structure, which has the same coefficients as one of the groups here. It will have 8 stages, and we take the known embedded pairs by Dorman and Prince, one of order 6 with an estimator of order 5 and 8 stages, and another of order 5, which is less than the constructed, but which have the same number of stages for most of the equations. So, we solve them in some interval with different absolute local error tolerances, and we compare the global precision, global accuracy to the number of steps done and to number of right-hand side evaluations, comparing each equation separately. So here the red line being the lowest one show that the best accuracy can be obtained with less computations than for other methods. And here even the number of steps done is fewer, and the number of stage right-hand side evaluations is much fewer than in the known methods. So this is motivating to continue studies of such methods and searching the systems to apply them. So thank you for your attention. If you're interested, some references could be sent or they are presented in the published version of this talk. Thank you.
Okay. Any questions, please? If there are no more questions, I will adjourn.
There is a question in chat.
Okay, I cannot see.
When will we use this method in a math package?
Well, we haven't proposed this method to be like a built-in in mathematical packages. We have implemented it in MATLAB, and well, it performs quite well, but it always very dependent on how many equations can we include in this part of in those structural groups. And honestly, not so many models have a large number of equations to be included in those groups. So it's a good academic style work, but we will be very thankful if someone finds more systems like this, so we could use them as an examples.
Okay, thank you. And I have also a question. Is there a name of this type of special structure for the system?
Oh, well, they were introduced and studied mostly by Professor Olemskoy, so maybe one day they will be called in his honor, but right now we just call them structural methods.
I think you should do this for Professor Olemskoy. Thank you.
Okay, Alexander, say please the final word of the session.
I will adjourn this meeting. Thank you for participating. Goodbye.
Okay, thank you everyone. In 15 minutes here we will start another session, methods for analysis and design of systems with time delay, part 1.
весна, а небо хмурится, дождит с утра до ночи, и серой плотной пеленой под проливным дождем. И там, и тут осинки ждут, закрылись небо очи. И там, и тут лучей крылатых мы с нетерпением ждем. Лишь ручьи дождю и небу хвалу поют, лишь они не напились и пьют, и пьют, пьют, и пьют. Лишь ручьи дождю и небо хвалу поют, лишь они не напились и пьют, и пьют, и пьют, и пьют. Лишь ручьи дождю и небо хвалу поют, лишь они не напились и пьют, и пьют, и пьют, и пьют.
Первые шаги. Каждый начинает так свои круги. Вот еще ступенька, лестница и злом. Тут и поджидает нас первый перелом. Тут и поджидает нас первый перелом. На этаж поднялся, делай поворот. Видишь, как к вершинам движется народ. А ступени круче, каверзней и злом. Каждому не просто двигать напролом. Каждому не просто двигать напролом. Повороты, марши и снова поворот. На седьмое небо нас всегда влечет. На пути бывает встретится пролом. Нет ступеней, вот последний перелом. Нет ступеней, вот последний перелом. Дальше нет дороги, лезем мы с стене. И если не сорвемся, будем на коне. Вот 7-е небо, я ищу коня, но рука другая впереди меня. Вот 7-е небо, я ищу коня, но рука другая впереди меня. Терпит лук от тетива, зато стрела летит далеко. Терпит тень в лесу трава, хоть и тянется высоко. Терпит тихая волна, когда ее ломают руки. Терпит тонкая струна для тебя, рождая звуки. Мне не терпится в жару хрустальных вод, спешу напиться. Мне не терпится в миру, горе любовь во мне искрится. Мне не терпится в жару хрустальных вод, спешу напиться. Мне не терпится в миру, во мне искрится. Не могу в тени я быть, когда по небу солнце ходит, и по воле волн не плыть, тоже очень не подходит. Где же мне найти тебя и позабыть все прегрешения? Я скажу тогда, любя, ты одна, мое спасение. Мне не терпится в жару хрустальных вод, спешу напиться. Мне не терпится в миру, ой, любовь во мне искрится. Мне не терпится в жару хрустальных вод, спешу напиться. Мне не терпится в миру, ой, любовь во мне искрится. Мне не терпится в жару хрустальных вод, спешу напиться. Мне не терпится в миру, ой, любовь во мне искрится. Мне не терпится в жару хрустальных вод, спешу напиться. Мне не терпится в миру, ой, любовь во мне искрится. Мне не терпится в миру, ой, любовь во мне искрится. призрак, звук пустой, ложный слепок детства. Бедный город мой тяготит мне плечи, бремя стольких лет. Смысла в этой встрече на поверку нет. Здесь теперь другое небо за окном, дымно-голубое с белым голубком. Здесь лежат другие тени и в пыли удар костерок осенний развели. Резко, слишком резко издали видна рдеется навеска в прорези окна. И не узнавая, смотрит мне во след маска восковая тех ушедших лет. Здесь теперь другое небо за окном, дымно-голубое с белым голубком. Здесь лежат другие тени и в пыли удар костерок осенний развели.
Алексей Петрович, включите, пожалуйста, микрофон. Мы ждем вас для начала секции. Okay. Dear colleagues, my name is Alexey Remin and I am moderator of this session. 4 talks will be presented here. All presentations are in English and please, not more than 12 minutes are given for every presentation. 2 minutes before the end, I will give you a voice notion. After that, there will be 3 minutes for questions. During the presentation, the audience will be muted, but you can unmute yourself after the presentations and give the questions. Also, you can pose the questions through chat and through the chat in the YouTube translation. Дорогие коллеги, меня зовут Алексей Ремин, я буду модератором этой секции. У нас будет 4 доклада по 15 минут, 12 минут на доклад и 3 минуты на вопросы. После презентации можно будет, соответственно, разблокировать микрофон и задать эти вопросы, или можно задать вопросы в письменной форме через чат. The chair of this session is Professor Alexey Zhabko. Alexey Petrovich, please.
Вот так. Слышно меня, да?
Да, да.
Alexei, where is Vladimir Razvan?
Здравствуйте.
Oh, okay.
Okay. Well,
Владимир, может быть, вы будете первым лицом вести, да? Так будет.
Да, потому что я должен представить вас.
Ладно?
Хорошо.
Спасибо.
Мы можем начинать?
Да, я думаю, что можем начинать. Вот руководите тогда процессом.
Хорошо. So, dear colleagues, welcome to our session, and allow me to introduce the first report, an algorithm for solving local boundary value problems with perturbations and delayed control, authorized by Alexander Kvitko, Alexey Eryomin, and Oksana Firyulina. Who will be the presenter? I suppose Alexey Eryomin.
no, it will be presented by Alexander Kvitko.
Okay, so you are in, as we say.
Александр Николаевич, начинайте, пожалуйста.
Yes, thank you. You see my report? Oh, no. Tell me, please, you see my report?
Yes, everything's okay.
My report is named an algorithm for solving the local boundary value problems with perturbations and delayed control. My co-authors are Alexey Eryomin and Oksana Firyulina. Problem statement. Consider an online stationary controlled system of ordinary differential equations with a delay H monal in the control and constant perturbation F. This system have kind 1, where X is n-dimension vector and the control U is r-dimension vector such that r less than n. The right-hand side function f are satisfying conditions. Is satisfying conditions 2, 3, 4. Norma U is bounded. Yes. Problem 1. Find a differentiable control U of t and differential function of phase states x of t satisfying 1 and the following conditions. Initial conditions 5. Stabilization conditions. For any small epsilon monal, there exists some moment t bar satisfying conditions 1 minus t bar less epsilon z, norma x of t bar less than epsilon. The control starts at the initial time. Condition 6. The main result of the paper is theorem 1. Let the right-hand side of 1 satisfy the conditions 2, 3, 4. Then for any epsilon monal there exist constants epsilon null 1 monal, epsilon null 2 monal, and epsilon null 3 monal, such that for any initial point x so that norma x bar so that norma x bar less than epsilon null 1, any perturbation f so that norma f less epsilon null 2, and any delay h belong interval null epsilon null 3, there exists a solution of problem 1 which can be obtained by solving a stabilization problem for a linear non-stationary system with exponential coefficients, followed by solving an auxiliary initial problem for a system of ordinary differential equations. The dimensions of both systems are n plus r. Theorem proof overview. In 810, it was shown that in case H equal null, even stronger theorem can be proved. Then algorithm of constructive U of t and x of t such that x of 1 was given. Here we at first consider the system 1 without delay, namely H equal null, and then estimate for which H value the system can be transferred to the epsilon neighborhood of null. Null is vector null. We make a change of time t to tau according to formula. So the system 1 takes form 7, where y of tau is an dimension vector equal x of t of tau, and W of tau equal U of t of tau. The function f in 7 is then expanded into Taylor series at the point 9 null, and for n shifts of phase coordinates are made. The goal of the shifts is to make the norms of those terms in the right-hand side of 7 that don't explicitly contain powers of y and w components satisfy the estimate. For details, see 810. 810 is reference. After shift, the system takes form 8. The z of tau is a vector for new phase coordinates. W of tau equal U of t of tau is a control in tau variables. P is n product n matrix, Q is n product R matrix, which are depends on tau, alpha, and f. And the initial condition z of null depends on x bar and f as well. The vector R contains the terms that can be shown to satisfy condition. R depends null as tau depends to infinity if norma z and norma w are bounded. We introduce an auxiliary control function mu of tau such that satisfying differential equation 9. And we set W of null equal null. Then we can consider the linear part of 8 together with 9 to be a controlled system 10. It is shown that under the condition 4, there exists epsilon 2 monal such that for if norma f less than epsilon 2, there exists a control function mu of tau of kind 11. This control guarantees the exponential decay of the fundamental matrix of the system 10 closed with it. After solving the stabilization problem for 10, we find the solution of the initial value problem 8, 9 closed by the auxiliary control function 11 at certain interval now tau bar, where tau bar depends on epsilon. This explicitly gives the expression of nu as a function of variables tau via 11. Finally, we consider initial problem for system 20. The final part of the theorem 1 proof that shows that for any epsilon null there exists a non-zero delays H, providing transfer of the system to epsilon neighborhood of null. Null is vector. Null by some T bar belong interval 1 minus epsilon 1 has not been presented in previous works. Its idea is to substitute W bar of tau equal U of T of tau minus H instead of W of tau equal U of T of tau into the right-hand side of 8 and study the behavior of such system closed with the sum control 11. However, we don't include it to present paper due the paper size restrictions.
One minute, please.
Test example. As an example of presented algorithm application, consider the problem of controlling a manipulator when transporting a load to a given point. According to one is reference, the system of equation describing the motion of manipulator in presence of perturbation has form 13, where x1 is manipulator deviation angle from the vertical axis, x2 is an deflection angle changing rate, A1, A2, M1, M large is parameter system. L F large is perturbation. We consider scalar control U. We consider the boundary conditions 14. In this case, the system 189 takes form 15. This matrix M of tau. After substituting of new equal M product vector Z1, Z2 W to 15, we get the initial value problem with Z1 of now equal Z2.
Alexander Nikolaevich, finish, please.
Figure 1 shows the solution for x1, x2, new L, M, M0, F, value epsilon, choose alpha, H. On figure 1, figures 1 contain graphics of control function U and phase state functions x1, x2. That's all. Thank you for attention.
Are there any questions, discussions?
No question. Thank you very much.
Thank you. So we can pass to the next talk, authored by Alexey Petrovich Zhabko, Olga Chizhova, and Oleg Tikhomirov, the prediction scheme to the linear systems with linearly increasing and constant delays.
Ольга Чижова докладывает.
Остановите демонстрацию.
Ой, спасибо, Алексей. Я остановил.
Good afternoon, colleagues. At first, I must apologize to you. Unfortunately, the camera in my laptop is not functioning, and you don't see me now. Now I am presenting the research, the prediction scheme to the linear systems with linear increasing and constant delays of the authors Professor Жабко Алексей Petrovich, Associate Professor Tikhomirov Oleg Gennadievich, and Associate Professor Чижова Ольга Николаевна. We investigated the mathematical models of dynamic processes described by systems of differential difference equations of delay type with constant input delay and unbounded state delay. The focus is on the problem of stabilizing control design for these systems. Because of the state delay is unbounded, then several well-known approaches are not applicable for stability analysis of such systems. The main goal of this paper is the application of the new approach for the construction of the stabilizing control. It is based on compensation of the state delay in the construction of stabilizing controller. In the research, we applied the prediction scheme for the compensation of the state delay and considered the possibility of the control construction. Now we consider the system number 1. Dimension of the state vector x is n. Dimension of the input vector u is m no more than n. A0, A1, and B are constant real matrices. T0 is initial time instant, tau is positive constant input delay, and H is linear increasing state delay. Now we assume that the initial function phi belongs to the space of piecewise continuous functions and introduce shown designation for the restriction of the solution. Professor Kharitonov, in the paper An Extension of the Prediction Scheme to the Case of Systems with Both Input and State Delay, studied the systems with constant state delay h no more than constant input delay tau. He assumed that there exist the matrices F0 and F1 such that the system number 2 is exponentially stable. Then he constructed a control law under which system number 3 coincides with system number 2 for t more than tau. Now we consider the system number 1 again. We assume preliminarily that there exist the matrices F0 and F1 such that the closed-loop system number 4 is asymptotically stable. In the paper, Robust Stability of Differential Difference Systems with Linear Time Delay, the system number 5 was investigated. The conditions of asymptotic stability such systems were obtained in this paper. The system 5 is asymptotically stable if the corresponding system without time delay is exponentially stable and the shown difference system is asymptotically stable. In accordance with indicated paper of Professor Kharitonov, we consider an auxiliary system number 6 and a compensating control in the form 7. Now we can write the characteristic polynomial of the linear system 6 and 7 and transform it. After transformation, it has a shown form, this form. Now we will prove an auxiliary lemma. If the matrix A0 plus BF0 is satisfied Hurwitz criterion and the eigenvalues of the shown matrix are in the unit circle on the complex plane, then there exist two matrices C and D such that the difference system number 8 is exponentially stable for sigma more than 0. We will show that all roots of the characteristic polynomial of the system number 8 are in the unit circle on the complex plane. In this paper, we will consider only a case where the matrices A0 and A1 minus A0 minus BF0 have not zero eigenvalues. Then we can show that the characteristic polynomial of the system 8 has this form. Now we transform the matrix. We add the first column to n plus first one, the second column to n plus second one, and so on. As a result, we obtain the next form of the characteristic polynomial. Then we construct the matrices C and D by the equalities number 9. This matrix will be chosen later. Now we can transform the characteristic polynomial system 8 again. As a result, we obtain it on the next form. Let us note that the first multiplier is the characteristic polynomial of the closed loop difference system. As we have seen in the system number 5, the matrices F0 and F1 are chosen such that all roots of this multiplier are in the unit circle on the complex plane. Now we consider the second multiplier. We apply the formula of Frobenius to the determinant of the block structure matrices and transform the second multiplier to the next form. Now we choose the matrix, this matrix, by the equality 10. Then this matrix will be the 0, 1. And we can show that the second multiplier of the characteristic polynomial has 0 roots only. This ends the proof of lemma. Now we use the lemma and the control 7 to solve the stabilizing problem for system 1. We will consider the system number 11. We can note that it is the system 1 with the compensating control. We assume that the following conditions are satisfied. The first condition, there exist the matrices F0 and F1 such that the matrix A0 plus BF0 satisfies Hurwitz criterion, and the eigenvalues of the shown matrix, this matrix are in the unit circle on the complex plane. The second condition, the matrices C and D are defined by the equalities 9 and 10. And the last condition, the matrices A0 and A1 minus A0 minus BF0 have not zero eigenvalues. Now we will prove that the system 11 is asymptotically stable. We will use the method of difference transformation. The method is successfully applied for such problems as controllability, observability, and stabilization. Is based on the fact that the solution of the system number 11 has k continuous derivatives for large enough values t. Therefore, we differentiate the system 11 k times and introduce the indicated notations, these notations. In accordance with the paper, The Stability of Different Systems with Linear Increasing Time Delay, we obtain the system number 12. The parameter alpha more than 0 and less than 1. Let k tends to infinity, then we obtain the system 13. This system is exponentially stable as the auxiliary system 6-7 or the slide 9 was exponentially stable. In accordance with indicated paper, there exists the number n such that the system 12 be asymptotically stable for k more than n. Now, we use the indicated equalities and transform the system 12 into the form 14. We can say that we rewrite technically the system 12 as a linear, unhomogeneous difference system. As we have shown, the right part of the first equality tends to 0, and the right part, this part of the second equality tends to 0 as t tends to infinity. The homogeneous part of system 14 coincides with system 8 for sigma equal 1 minus alpha multiplied by t, and the summands with delay have the multiplier alpha in degree k. So, if the eigenvalues of system 8 are in the unit circle on the complex plane, then the eigenvalues of homogeneous part of system 14 be in the same place for k equals 0, 1, 2, and so on until n. This ends the proof. All solutions of the system 14 tends to 0 for k equal n, so indicated relations take place as t tends to infinity. Then we consider the system 14 for k equal n minus 1, n minus 2, and so on until 0. As a result, we obtain that x tends to 0 and v tends to 0 for t tends to infinity. Now, the system 11 is asymptotically stable. Now we have solved of the stabilizing problem. The system of differential difference equations of delay type with constant input delay and unbounded state delay is investigated. The prediction scheme for compensation of the state delay is applied. The stabilizing control is obtained. Thank you for your attention.
Thank you. Are there any comments, questions, remarks?
Olga Nikolaevna, do you have example, any example, maybe for a dynamical, for a mechanical system?
For a mechanical system, I can say that in recent times, many new applications have appeared. For example, the traffic on the ringway. We investigated such mathematical model 2 or 3 years ago.
Thank you.
Thank you. Other discussions?
Or we don't have time for further discussion.
If not, I suppose we can pass to the next presentation belonging to Alexey Egorov, the generalized Mishkin's problem for a linear time delay system with time varying delay.
Thank you, Vladimir Germanovich. Let me start. So my talk, my talk is about the generalized Mishkis problem. We consider this system, the system star. Here matrix A is a constant real n by n matrix, and X is also real. It's a vector function of dimension n. Tau is a delay. It's assumed to be bounded by 0 from below and by h from above. Without any loss of generality, we can assume that h is equal to 1. Otherwise, we can make a scale of the time axis to get h to be equal to 1. The most popular approach for the stability analysis of system star, there are different approaches, but most of them reduce the task to some LMI problems. LMI means linear matrix inequalities. Our purpose was to give an alternative method, an alternative to LMI approach. In this paper, we reduce the task to a convex quadratic problem of quadratic programming. We start from a nice result of Mishkis. It's the so-called 3/2 theorem. Here, a scalar equation is considered, not the system. Number A here is a scalar real number. So the statement of the theorem says the following. If number A satisfies these inequalities, then the equation is uniformly stable for any bounded delay. The delay is still bounded by 0 and 1. Opposite, if A violates this condition, then there exists a delay which is still bounded, but the equation is unstable. In this sense, this boundary minus 3/2 can be considered as an exact stability bounded for this sort of delay-independent problem. Inspired by this theorem, we introduce the following definition. Matrix A solves the generalized Mishkis problem if system star is uniformly stable for any admissible delay. What does mean admissible delay? We will specify later. Our approach is based on the Razumikhin theorem, but on a modification of the theorem, which can be found in book of Kolmanovsky-Mishkis, 1999. If here we take n capital to be equal to 1, then we get the classical Razumikhin theorem, where we need to take a positive definite function, normally quadratic if we consider linear system. Then we need to differentiate this positive function along some special solutions satisfying the Razumikhin condition, which is this one. And to check negativity of this derivative. Here, n is not necessarily equal to 1, and if n is greater than 1, then the last condition doesn't degenerate, and this makes the following sense. N is an artificial delay, which is larger than the nominal delay, and if we take a larger delay, we need to continue the initial functions. We continue them by this last formula. In our approach, we take n to be equal to 3. Okay, so discuss the admissible delay. Function 2 is called the admissible delay if it satisfies 3 properties. First 2 properties are standard. They are the same like in Mishkis theorem, piecewise continuity of the delay and boundedness of the delay. But we also need the third condition because of our approach. Our approach doesn't work without this third condition. What this condition geometrically means? It means that the delay tau can decrease with any rate, but it can grow only with rate not greater than identity function, not greater than 1. In particular, if tau is continuously differentiable, then this condition is equivalent to derivative of tau is not greater than 1. If tau has discontinuity points, then the jumps at discontinuity points are negative. So all the jumps are jumps down, not up. And I repeat the main definition. A solves the generalized Mishkin's problem if a system star is uniformly stable for any admissible delay. This is the main theorem that has been obtained with the Razumihin theorem for n to be equal to 3. Matrix A solves the generalized Mishkin's problem if, so it's sufficient condition, if two conditions hold. First one, matrix A plus A transpose is negative semi-definite, and the second one is set omega of A is empty. Omega of A is a set of solutions of the system delta. These are algebraic conditions, but the problem is that system delta is not convex. So it's an NP-hard problem to verify whether the set of solutions is empty or not. Of course, it's not satisfying. And our purpose was to construct a new system which is convex, and any solution of system delta, of nominal system, is also a solution of the new system. So the set of solutions of the new system will contain a set of omega. And if the new set is empty, set omega is also empty. We have to separate two cases. Here we consider only first case. The second case can be considered very similar and lead to a similar result. So in the first case, if matrix A square by norm is greater or equal to norm of A, then system delta, nominal system, is equivalent to this one. It's simpler, but it's still non-convex. It's easy to show that any solution of the system satisfies also four inequalities on the slide. We introduced new variables. Before we had variables gamma and mu, and the number of components was 2n. Now it's n square. Vec here means vectorization. So it can be obtained by staking each column of the matrix gamma mu transpose on top of one another. With these new variables, we can express all the elements of system delta as follows. And we get the new system. This system is convex. It contains two square inequalities, which are both convex, and four linear inequalities, which are also convex for sure. This problem, so the problem is now to check whether the system has solution or not. This problem can be reduced to the following QC-QP problem, quadratically constrained quadratic program. We need to minimize function f, which is quadratic and convex, subject to one convex quadratic inequality and four linear inequalities. And we get the following theorem. Matrix A solves the generalized Mishkin's problem if matrix A plus A transpose is negative semi-definite, and the optimal solution x star of this QC-QP task is such that f of x star is not less than r. This problem is rather standard. It can be solved in a polynomial time. So now it's more or less the same in the sense of complexity, like LMI, which are usually exploited for the stability analysis of linear systems, and not only linear. If we also consider the second case, we get a similar result. So in the first case, we need to solve one QC-QP problem. In the second case, we need to solve two problems. First is also QCQP, and it's very similar to the one that I presented. And the second one is even simpler. It's a linearly constrained quadratic programming problem. So it's also P-complete task. Here is an example. We consider a special matrix A, 2 by 2 matrix with two parameters, alpha and beta. The solid curve on the figure, it's a boundary for the solvability of the Myshkis, generalized Myshkis problem, which was obtained recently in our paper. It has been obtained by a different approach, by an analytic approach, which is focused on this special case with such matrix A. Here, points in the figure corresponds to the new approach, which is numerical and that I presented now. So as you can see, if beta is small or even beta is equal to 0, then we have exactly the same result as the Myshkis theorem. So all the rightmost point is 3/2, like in Myshkis theorem. If beta is not equal to 0, this is not so good. The result's not so good, but still not bad in our opinion. That's all. Thank you.
Thank you for your talk. Remarks, discussion.
Alexei, can your approach be used to analyze systems with a time delay separated from 0? No, for example, delay belong to segment AB, A more 0.
Yeah, I had this idea. So our previous approach, which is analytical, can be generalized to the case of separated H. This new approach, numerical approach, I didn't try yet, so I don't know actually.
Thank you.
I have a question. Does this last picture show that the numerical approach and the analytical approach give different results and that one of them might be wrong?
If we're talking about this solid line, we are not sure that this is the exact boundary, but we are sure that this is very close to the exact boundary because there are some estimates. There is an upper estimate for this exact boundary, and this is very close to the obtained. So we are more or less sure that the solid line is close to the exact boundary for the solvability of the generalized Myshkis problem. About this new result, we have our purpose was to get a simple result, simple numerical approach. Introducing the new variables, you remember this X is new variables. We have more variables in the new system than in the previous one. So for sure that gives some conservatism to the result. And it's quite expected that our new approach doesn't give the whole region, just a part of this region. Hopefully I answered, Alexei.
So that's sufficient, but not necessary. Okay.
Yes, it's sufficient, not necessary. As the solid line, maybe it's necessary as well, but we have not proved, neither proved nor disproved this yet.
Okay, thank you.
Thank you. Other discussions? Well, if not, we have the fourth lecture of this subsection on the stability of linear time delay systems with arbitrary delays, authored by Irina Alexandrovna and Sabine Mondier from Sinvestav, Mexico. I suppose the paper will be presented by Irina Alexandrovna.
Yes. 1 minute. Can you hear me? Well, can you hear me?
Yes, yes.
Yes.
Please.
Okay, well, then I start. My name is Irina, and I'm going to present our joint work with which was done in collaboration with my Mexico colleague, Sabine Mandia. Okay, in this work, we focus on linear system with several delays. The system is time invariant, so the matrices and the delays are constant. And some standard notation some standard notations are listed below. And H large denotes the maximal value of delay in the system. Well, what's the problem? In the framework of Lyapunov-Krasovsky functionals with prescribed derivative, the following necessary stability conditions are known. The authors are Alexey Egorov and Sabine Mandia. What is nice in these conditions is that the stability of system 1 is expressed just in terms of one matrix U, which is known as the delay Lyapunov matrix. And if system 1 is exponentially stable, then such block matrix KR, composed of the delay Lyapunov matrix in different arguments, such block matrix is always positive definite if the system is exponentially stable. Here there are some examples on how the conditions of theorem 1 may look like, but theorem 1 is not limited to the conditions of this type because the points tau j here are arbitrary. So what is the delay Lyapunov matrix U? By definition, the matrix U is a solution of this matrix differential equation, which also satisfies this symmetry condition and the special boundary condition, which is called the algebraic condition. So the Lyapunov matrix is the matrix satisfying these three conditions simultaneously. If we are going to verify theorem 1, we need to compute the Lyapunov matrix. And for its computations, at the moment, an effective procedure is known just for the case of system star, where all delays are multiples by multiples of one basic delay h. In this case, it is possible to reduce these three properties from the definition of Lyapunov matrix to standard initial value problem for linear system of ordinary differential equations. So the Lyapunov matrix is in fact the matrix exponential with this matrix A. However, what are the problematic cases here for computation of the Lyapunov matrix? First, even if we can reduce system 1 to this system star, the number of delays, M1 here, can be unreasonably large. So even if, for example, the original system had just 2 delays, this value of M1 can be large. And there is the problematic case when the delays in system 1 are incommensurate, what means that there exist 2 delays whose ratio is an irrational number. In this case, there is no possibility to reduce system 1 to this form star. And in this case, we don't have an exact procedure to compute the Lyapunov matrix. So the aim of this work is to overcome this difficulty and to suggest an approach for stability analysis, which is based on the Lyapunov matrix, but which works for the case of incommensurate delays in the system. So the idea is that together with system 1, we consider an auxiliary system 2. Here in system 2, the matrices are the same as in system 1, and the delays are different. Well, the zero delay is assumed to be equal to 0 in both systems, and the other delays are assumed to be close enough to the delays of the original system, but the sense of this closeness, in which sense close, this question will be discussed later. And the problem is to find the necessary stability conditions for system 1, the conditions of the same kind as theorem 1, but the conditions based on the Lyapunov matrix of different system, the Lyapunov matrix of auxiliary system 2. So we assume that we don't know the Lyapunov matrix U of system 1, but we know the Lyapunov matrix of some close, in some sense, system 2, and we denote this second Lyapunov matrix by U hat. And our aim is to express stability conditions for system 1 via the matrix U hat. We take the standard functional with a derivative set by a negative definite quadratic form of x. For this functional, an exact construction is known, and it depends on the Lyapunov matrix U. And what we are doing here, we replace the matrix U here in the functional by the Lyapunov matrix of different systems. So in this functional, the integration limit and all parameters, all arguments correspond to the original system 1, and the only Lyapunov matrix is different. This is the Lyapunov matrix of different systems. And actually, the idea to use this functional is not new, and there are a couple of works where this idea was already exploited. Well, we take this functional and we differentiate it along the solutions of the original system 1. And we obtain that the derivative is still that quadratic form from which we started, and plus some additional functional. And this functional can be estimated by the expression of this form. And here the constants xi0 and xij, they depend on the same expression f. And what is f? The expression for f is here. It contains the differences between the values of Lyapunov matrix in different arguments. These are delays of original systems, and these are delays of the auxiliary system. So difference between the delays and closeness of the delays, it is hidden here in the expression of f. And now we introduce our assumption. First, we assume that the auxiliary system 2 satisfies the Lyapunov condition. This is the condition for existence of the Lyapunov matrix U hat. And second inequality 3. We see that this assumption is related to the derivative of the functional. And we remember that this constant xi, they contain the difference between the delays of the original system and the delays of the auxiliary system. So this condition 3 is the condition on the closeness between the delays of two systems. We assume that it holds. And now the functional v0 is not enough to use. We need to add an additional summand into this functional. Here we have function omega, which depends on that values xi, which contain the differences between the delays. And one can note that under our assumption, here in the last summand, we always have a positive definite matrix in the functional. And because of this fact, we are able to prove these two lemmas. The first lemma is about the derivative of this functional along the solutions of system 1. This is the negative definite quadratic form of this vector. So the matrix here is positive definite, once again, due to our assumption. And if our assumption holds, and if system 1 is exponentially stable, then this functional admits the positive lower bound of this form with the positive constant alpha here. So these lemmas together mean that our functional satisfies the classical Lyapunov-Krasovsky conditions. And in spite of the fact that we made a couple of modifications here, we took a different Lyapunov metrics and we took different expression here, this functional still is suitable for the stability analysis of system 1. So let us recall the basic idea of the original approach, how that necessary conditions were obtained. The function phi bar of special form was taken. This function depends on the fundamental matrix of the system and on some arbitrary vectors gamma. And after substitution of this function into the functional, well, the functional is a little bit different, but our functional coincides with that one if the delays of two systems coincide. So we substitute this function phi bar into the functional, and we obtain that the expression of the functional becomes a quadratic form of the vector gamma. And here the matrix of this quadratic form is that block matrix composed of the Lyapunov matrices, the matrix Kr. And the necessary condition of positive definiteness of this matrix Kr goes from here. So in our case, we exploit the same idea. We take the function phi bar, but because of the fact that our functional now depends on different Lyapunov matrix U hat, here we have also different fundamental matrix. This is the fundamental matrix of auxiliary system 2. And then we substitute this function into our functional, and we obtain once again that the functional becomes a quadratic form of the vector gamma. But what is the matrix of this quadratic form? It is composed of two parts. The first part here is what was expected and what is desired. This is the block matrix contained of the Lyapunov matrix U hat, the Lyapunov matrix of the auxiliary system. And because of the fact that the Lyapunov matrix and the fundamental matrix are now different, we have here the matrix delta, which also has a block structure. And this is a matrix, let's say, of some discrepancies that appear in the properties that we use in the proof. Let us give a brief look into the structure of that block delta. So here we have dependence on the fundamental matrix of the auxiliary system, on the Lyapunov matrix of the auxiliary system. And what is important here, that if we for a moment assume that the delays in two systems coincide, so H are the same as H hats, then all summands here disappear, and this matrix is equal to zero matrix. So when the delays are close, this matrix is supposed to be small. And so finally, we obtain the result that under our assumption, the necessary stability condition for system 1 is positive definiteness of this block matrix, which is composed of two parts, blocks of Lyapunov matrix of the auxiliary system, and that blocks delta that can be shown, that were shown on the previous slide.
Irina, it's time to finish.
And now I'm going briefly to show the example how to apply these conditions. So, for example, we consider the scalar equation, and these are the stability charts in the space of parameters B and C. So to apply our conditions, we need first to check an assumption, and pink points correspond to the points where assumption holds, and red points correspond to the cases where assumption holds and our necessary stability condition also holds. So here R is equal to 2, and here R is equal to 5. And here these are the same stability charts, but for different value of h hat, which is much closer to the delay in the original system. And what we see the kind of convergence here. So we have many areas where necessary condition hold for R equal to 2. Then we have just 2 areas for R equal to 4. And for R equal to 5, it seems that we obtain necessary and sufficient stability condition under our assumption. So we can see the kind of convergence here. And it is worth of mention that this kind of convergence was in the original necessary stability conditions. And so the direction for future research is to try to prove this convergence to the necessary and sufficient conditions. That's all. Thank you for your attention.
I have a question.
Yes.
This nice result, thank you, Irina. How fast is the algorithm? So, I mean, computation of this matrix delta, how is this slow or not?
Actually, it is not fast, unfortunately, because of the fact that we can see here there are a couple of integrals of fundamental matrix and of Lyapunov matrix. So this is not fast. One of the possible approaches is to estimate the fundamental matrix and the Lyapunov matrix here. So not the compute all the integrals, but compute some estimation of this matrix. But in this case, we lose convergence because we obtain the dimension of the matrix R, we obtain is as a multiplier in the estimate.
But I see that the number R is quite small in your examples.
Yes, but if you have R, suppose that we have not the matrix delta here, but some estimate for it, and the R is multiplier here. So if you multiply this by 5, for example, then you lose convergence and you will not see nice picture like this.
Mm-hmm. Okay, thank you.
Are there any comments? I would like to make a comment if possible.
Yes, of course.
Could you view this problem on some other point of view to consider that the non-commensurable delays introduce with respect to some commensurable some persistent perturbations, and to use some Malkin type results for concerning stability with respect to persistent perturbations? Would it be possible such things? Have you thought about such a possibility?
So you mean to have some nominal system, yes, and to consider some perturbations in the delay?
Nominal to be rationally dependent, and with respect to it, the difference of the two terms to be rationally independent. From continuity, this difference is small enough.
Yes,
so
but
it looks like a persistent perturbation and use the theory of Malkin adapted to time delay systems. It's just thinking about the history.
Yes, but this is a different approach to the same problem.
It's a different, of course. So it is for reflection.
Yeah, thank you.
Thank you. Other discussions for this paper? Now, how shall we proceed for the second part of the session?
We should wait. We should wait for 4:30.
at 4:30. We shall meet again here in this room.
Yes.
So I will remain on it and wait. And who will be the chairman? I suppose now Alexey Petrovich.
It's up to you.
Well, I suggest to be the same, to be together, co-chairman. It's his time now.
Okay. Okay, so Alexey Petrovich for the next.
Okay. We have 7 minutes. Так, в половину мы встречаемся, да, Алексей?
Да.
Угу. Ну ладно.
Сменяйте золото мое на мудрость старости глубокой. В бокал налей ты мне питье и дай мне хлеб рукой высокой, как ты давал ученикам в тумане древности столетий. Любви учил, любви к врагам, прошло уж столько лихолетий. И ломтик хлеба, и вино, сокровищ всех ценней на свете. Любви в них столько нам дано, что хватит всем на всей планете. И ломтик хлеба, и вино, сокровищ всех ценней на свете. Любви в них столько нам дано, что хватит всем на всей планете. Сменяйте золото мое на мудрость старости глубокой. В бокал налей ты мне питье и дай мне хлеб рукой высокой. В бокал налей ты мне питье и дай мне хлеб рукой высокой. Летят невиданные сани, на облучке сидит судьба. Мы выбираем место сами, и начинается борьба. С утра судьбу мы погоняем, бросаем сани вверх и вниз, ума по лужню набираем, и только думаем, держись! Ума по лужню набираем, и только думаем, держись! Идет уж вечер, мы устали, забыты юности дела. Неугомонными промчали, зачем борьба с судьбой была. Над нами крылья темной ночи, ведут сыны и внуки бой. Когда под пять открыть нам очи, судьбы не выбрали б иной. опять открыть нам очи, судьбы не выбрали иной. С утра судьбу мы погоняем, бросаем сани вверх и вниз, умополую набираем, и только думаем, держись! Умополую набираем, и только думаем, держись!
Проходят годы безвозвратно, играет ветер серебром. Душа болит, но как приятно опять приехать в мамин дом. Летят года, судьба играет, а домик маленький стоит. Никто там не вздыхает, и след в окошках нет.
De care e vorba, era orb. Zubul înseamnă dinte. Nu. Я такого не ожидал, Алексей.
Владимир, вы сейчас с каким Алексеем общаетесь?
С вами?
Здравствуйте, Владимир.
Здравствуйте. Я знал, что Владимир Иванович писал стихи, но не знал, что они такие, что, как положено в России, песни по ним сложили.
Да, это была хорошая идея их включить в промежутках. Я думаю, мы можем начинать.
Я тоже так считаю, но
так, да.
Будет председательствовать Алексей Петрович или вы, потому что у меня нет...
Владимир, я начну тогда.
Прошу вас, Алексей Петрович.
Спасибо. Я, кстати, пока мы не начали, хочу поздравить Владимира с юбилеем. Я вас поздравляю с днем рождения, Володя.
Ну, это было в мае.
Но... Ну ничего, а мы же не были в мае там.
Ну, спасибо.
Вот, и рассчитываю, что на следующий год, так сказать, тут закончится, и мы тогда снова увидимся где-нибудь на конференции.
Я тоже надеюсь, понимаете?
Да.
Надеюсь.
Хорошо. The first report we have Alexey Lobatskin, Alexey Yeremin. Fourth order method, for differential equations with discrete and distributed delays. Кто будет? Александр, прошу прощения. Александр Лобаскин. Sorry.
Can you hear me?
Yes, I will try to start it.
Hello, everybody. My name is Alexander Lobaskin, and together with Alexei, we present the work on an application of the explicit Runge-Kutta method for integrated differential equation with discrete delay. In some fields of science, such as mathematical modeling in biology and medicine, population dynamics, epidemiology, immunology are considering these special differential equations to improve an accuracy of modeling. Consider a differential equation with discrete and distributed delay. To formulate an analog of the initial problem, equations require a prehistory function phi of t, defined on certain interval before the starting point. This equation can be viewed as an extension of Volterra's integral differential equations. A feature of such equations is that the lower limit of integration is not fixed and depends on time t or system state y of t, in contrast to the VIDE. And also the function f depends on the discrete delay y of alpha of t. Discrete delays may depend on time and system state, and also overlap the current step. The purpose of our work is to consider and modify the Tavernini method, develop its effective implementation for solving integral differential equations with discrete delays. The steps in our work are as follows: consider the general form of the Runge-Kutta methods for EDS with discrete delays, modify continuous stage Tavernini methods of convergence order 4 for the case of distributed delay, consider the problem of passing through the breakpoints of derivative, and develop a program. Consider the general form of the Runge-Kutta-Beltikov type method from Lyubich's article on the Volterra equations. The main difficulty in the numerical solution is the calculation of the integral f with wave. Consider the explicit four-order Beltikov method. It can be used as the main one, but it has a number of problems. It's not suitable for equations with state-dependent delays and overlapping problem. In the works of Massett and Tavernini, continuous stage methods were developed to solve these problems. The stage continuous Tavernini method of convergence order 4 was chosen as the main method. It was adapted to the methods of Beltikov. The Butcher table of this method is presented in table 2. Let's talk about calculating the integral. To save methods discrete order 4, we need third order condition approximation for the integral term. However, in Lyubich's article, multi-step trapezoidal interpolation was used. But due to the discrete delay, discontinuity points may appear, through which it's impossible to interpolate. The discrete order of the method may be lost. Therefore, to solve this problem, we used the local Hermite interpolation and Simpson's rule. At the mesh points, the solution itself and its derivative, the right side of equation, are known. Based on this data, it's possible to construct a local interpolation polynomial of the third order of accuracy. The integral is calculated at each step by the Simpson's rule over the mesh intervals from t0 to tk. Formula 7 allows finding the midpoints of the intervals of the solution, and then the integrand k in the middle of the segment. There is one more nuance. At the end of steps, we need to find the derivative in the next step. But for this, we need to find the integral from sigma of tk plus 1 to tk plus 1. Y of the middle of this step is missing for Simpson's rule. Therefore, we use the second order Hermite interpolation according to the available data. So Simpson's rule will be proportional to h cube, which is required. When the retarded arguments pass through the breakpoints of derivatives, new breakpoints of the derivatives of the solution of higher order appear. To detect and calculate them, the efficient algorithm presented in 2015 by Romin and Humphreys can be used. In order to verify the fourth convergence order of the constructed method, we run two tests with constant time steps h and check the global error to the time step ratio. We choose the test problems with known solutions, such that the delays are time and state dependent and overlapping occurs for the discrete delay. We choose the problems without discontinuities to make a pure convergence test unaffected by discontinuities detection and approximation algorithm. Consider the problem with overlapping happening at one or few first steps. We solve it over the interval 0 to 5 with constant step h equals 0.01 and calculate the global error E. And as it can be seen from figure 2b, the error behaves as h to the 4. This is a problem with two discrete delays, one of which is state-dependent and time-dependent delay sigma. As well as problem 1, we solve it over the interval 0 to 5 with constant step h equal 0.01 and calculate the global error E. Figures 3b show convergence of order 4. We solve it over the interval 0 to 5 with n constant steps h equal 5 by n and calculate the global error E as the maximum difference between the exact solution and its continuous approximation eta of t. Table 2 and table 4 shows convergence of order 4. I'd like to tell about the application of this equation in life. The first one is population dynamics. In Hal Smith's book about the use of DDE, delay differential equation, there is a model that describes a virus parasiting on bacteria. Of course, control theory when building PID controllers and time analysis. The second one are immunology and epidemiology. For example, characterizing chemotherapy induced neutropenia and monocytopenia through mathematical modeling by Cassidy and Anthony Humphreys. Third one, also from epidemiology. It's a mathematical model of infectious diseases with time delay or modified SIR model. Here are the results of solving this problem. Conclusions. annexation of the explicit method from Runge-Kutta of order 4 for VDE to the case of equations with discrete delay is considered. Modified Tavernini method for equation with discrete delay, a variant of calculating the delay used to the Hermite interpolation polynomial is proposed, due to which it's possible to approximate the integral, to speed the breakpoints of the derivatives of the solution, and numerical solutions, for example, confirm the fourth convergence order on problems with overlapping and state-dependent delay. We consider the direction of development of the work results to be the construction of stage continuous Runge-Kutta method with the third order error estimator for constructing a method with a variable step length. It's planned to solve pair trainable equations with integral equations, as well as to consider implicit methods for solving stiff problems. This slide provides a list of references. And that's all. Thank you.
Thank you very much. Any questions?
I have one question. Alexander, could you show the slide with the second example with the state dependent? Yes, this one. So did you check, is this, in which interval do you solve this equation?
Извините, я пока плохо ориентируюсь.
А на каком интервале вы решаете уравнение?
На интервале от 0 до 5 решаете. Да.
И на этом интервале у вас действительно аргумент не опережает время, да? То есть действительно запаздывающий тип получается. Проверяли, да?
Ну да.
Для достаточно малого шага, да.
Окей, thank you.
Any questions? Maybe comment? Thank you very much.
Thank you.
Our next report,
Okay,
Svetlana Kuptsova.
1 minute left, so...
Светлана Купцова, Сергей Купцов, Ульян Зараник. On asymptotic quest-send position in time delay system. Светлана, вы будете докладывать, да?
Да.
Okay.
Good evening, my dear colleagues, and let me present my talk. I would talk about asymptotic quiescent position in time delay system. And let me recall the history of this problem. The concept of the asymptotic quiescent position was introduced by Vladimir Ivanovich Zubov in the research of the behavior of solution of differential equation in the case when the system has an attracting but not invariant set. What does the asymptotic quiescent position mean? Let us review the meaning of this concept with the simple example. Проблемы.
Светлана, пожалуйста, на полный экран включите.
Oh, sorry. Let us consider the differential equation without delay. We see that this equation has asymptotically stable trivial solution. And obviously the functions v and w solve the problem of asymptotic stability in the large of this trivial solution. That is, all solution of equation 1 tends to 0 as t tends to infinity. Next, we consider the equation 3. The equation 3 has no trivial solution, but since the right-hand side of equation 3 differs little from the right-hand side of equation 1 for sufficiently large t, the assumption arises that the solution of equation 3 will also have property 2. If this property will be satisfied, then position x is equal to 0 will be an asymptotic quiescent position. And the following question appears, how to check if property 2 is performed? An idea arises to differentiate the same function v along the solution of, of equation 3 and to find out under what condition on its derivative condition 2 will be satisfied. The presented work is devoted to the study of a similar issue for system with delay. I would talk about time delay system where we have one delay h. We have function f of t, x, and y, which is continuous on the set, this one, and satisfy the Lipschitz condition with respect to the argument x and y. This is the concept of initial value problem for time delay system. Here we assume that the initial function phi belongs to the set of continuous vector function. And let us denote the space of continuous vector function by big X. I would like to use the Euclidean norm for vectors, and for initial function phi, I will use the uniform norm. And this is the concept of the state of the system for and now let us introduce the concept of asymptotic quiescent position. The position x is equal to 0 is called an asymptotic quiescent position for system 4 if there exists positive epsilon such that for all initial function phi with the norm is less than epsilon, the solution of initial value problem is defined on this set and tends to 0 as t tends to infinity. This is a local asymptotic quiescent position. And the position x is equal to 0 is called an asymptotic quiescent position in the large if all solutions of the system 4 are defined and have the property 5. Next, we will define several concepts that will be used in the following theorems. This is the concept of negative definiteness of the function on the certain set. Let us consider the function, continuous function lambda, and a function w of t and x is called negative definite on the set. The norm of x is greater than or equal lambda. If function w is continuous in the variables on the set, this one, and admits an upper bound of this form on the set, the norm x is greater than or equal to lambda, where the function w1 of x continuous and positive definite for all x from Rn. Now, let me remind you that there are 3 approaches to researching the stability of solution of time delay system. by the Lyapunov direct method. The first approach is the method of Lyapunov-Krasovsky functionals. The functionals play the role of Lyapunov functions. The second approach is the Razumikhin approach. Therefore, solving of the stability problem, use the function, but the derivative of this function along the solution is estimated not on the entire set of solution, but only on a certain subset of it. And the third approach is the junction of the first and the second methods. And in this work, we used the third approach. And so we need the concept of functional. Here by functional, we will mean the mapping of a set R1 plus times X2 into R1. And this is the definition of continuity functional. And this is the concept of derivative of the functional V or along the solution of the system 4. If we substitute if we substitute the solution of the system 4 into functional V, we get a function V of t. And by derivative of functional V along the solution of the system 4, we will mean the derivative of function V of t with respect to t. And we'll denote it like this. Further, we suppose that the function, the function phi, that the function f of tx and y is uniformly bounded in t on the set this one, and introduce the set S, which is consists of continuous function phi with the following property. And now I would like to present theorem 1. If for system 4 there exist the continuous functionals V and W, such that the functionals V admits a low bound of this form with the positive definite function V1, such that V1 of R tends to infinity as R tends to infinity. And it admits an upper bound of this form with the positive definite function V2. Here we see the norm of function in the space of continuous function. There exists a positive delta such that for all xi between t minus delta and t, the following inequality holds. For all functions belongs to the set S. The derivative of functional V along the solution of the system 4 admits an upper bound of this form, where the function W1 is negative definite on the set, the norm of X is greater than or equal lambda. Upper limits of this function is non-positive, and the function lambda of t, which is sitting here, is continuous positive and tends to 0 as t tends to infinity. Then x is equal to 0 is asymptotic quiescent position in the large foot trajectory system 4. And also we obtain a similar results for decision the problem of asymptotic stability of trivial solution. Here we assume that the system 4 has a trivial solution, and we abandon the condition that function f bounded in t. Here you see the same condition of the same condition on the functional v and w as in theorem 1. And if such functionals exist, then the trivial solution of system 4 is asymptotically stable. In conclusion, we give an illustrative example to theorem 1. Let us consider question 6, which has no trivial solution. And functional V of this form. And let us show that this functional satisfies all conditions of theorem 1. The first condition is performed since the functional V admits a lower bound and upper bound with this function tends to infinity as norm x tend to infinity. Thus, the first condition of theorem is satisfied. Let's check the second condition. For this, we consider the functional V along an arbitrary solution x of t. And we see that if function x sub t belongs to the set S, for all c between t minus h and t, the following inequality holds. And we consider the function gamma of t of this form. The derivative of function gamma is a positive value at point t, since the function x sub t belongs to the set S. Consequently, gamma of t increases at the point t. So both terms of function v increase at the point t, and the required delta from second condition there exists. Let us check the third condition of this theorem. This is it. If we calculate the derivative of functional v along the solution of equation 6, we get the functional w of t x sub t. Transforming this functional w, we obtain for it the following estimate. And as a function w1 of t and x, we take this function, and as a function lambda, we take this function. When we get the following estimation on the function w1, this estimation, on the set, the norm x is greater than or equal lambda. Thus, the third condition of theorem is satisfied. Let us check fourth condition. This is it. Let us estimate the function w1 on the set norm of lambda is less than lambda. That is, for this we substitute this estimation into function w1 instead of this function, and we discard the first term since it is negative. Thus, they obtain the following estimation on this function. And consequently, the fourth condition of the theorem is satisfied too. And obviously, that the fifth condition of theorem 1, this is it, with the function lambda of this form, is also satisfied. Therefore, all conditions of theorem 1 are satisfied, and the position x is equal to 0 is asymptotic quiescent position in the large for equation 6. And this is the literature that help us in our research. And thank you for attention.
Thank you very much. Questions? Any questions? Svetlana, could you compare your theorem for symptotic quiescence positions with theorem with usually theorem about asymptotic stability?
I don't understand question.
Если мы лямбда положим равным нулю, насколько они получатся слабее или будут совпадать с теми теоремами?
Тогда не имеет смысла ее здесь, в принципе, если лямбда будет равно нулю, тогда положительная, отрицательная определенность функции W, ну или функционала, да, W, если мы рассматриваем систему с запаздыванием, она будет во всем пространстве в этом случае. Вот. Поэтому здесь имеется в виду как раз, что за счет этой функции лямбда мы можем ослабить условия на отрицательную определенность производной. Вот. Поэтому здесь как раз
То есть тогда получается просто теорема об асимптотической устойчивости, так я понимаю?
Ну да, но тогда, если у нас не будет этой лямбды, тогда у нас будет отрицательная определенность производной. А здесь имеется в виду, что нас этот случай не очень интересует.
Не, ну я и просил сравнить.
Да.
Any comments? Владимир, ничего не хотите сказать? Включите звук. Как
мы не слышим.
Мы не слышим.
Вас не слышим.
Извините.
Вот, да, вот
сейчас есть старые результаты Страус и Йорк, которые называются Perturbation Results in Journal of Differential Equations, which are similar to these ones, not identical. Maybe this will become a classical problem, and it will be useful to look at them. If you don't have anything against, если у вас ничего нет против, я пошлю вам эти статьи, потому что они уже свободны по интернету.
Буду очень признательна. Thank you very much.
No, you are welcome, because it's very nice that you still work on classical problems, and clearly for me these results are new, are different of what I've seen.
Thank you.
You are welcome.
Any questions? Then we finish. Тогда заканчиваем, да? Вроде у нас сегодня наша вся работа, мы все доклады прослушали, работа наша выполнена, да?
Ну, оказывается, что это так.
Да. Ну, тогда на сегодня мы с вами прощаемся и завтра увидимся, наверное, и на пленарных докладах, да?
Хорошо. Всего доброго.
Всего доброго.
Пока.
До свидания.
До завтра. До свидания.